So I will give you a second part of these lectures. Jennifer will give the last part on Friday. So just I will give you a quick review. So let me run through that. So we are interested in should we consider two large graphs to be similar? What's the correct notion of a limit? And how do we model non-parametric models? I addressed this question at length. So here is the summary. In the most general setting, we can have some probability space. Think of it as a feature space in any dimension. You put some probability measure over it, and you have a graph. And then you choose your features IID at random. And then you connect the graphon, then says it's a probability of connecting if you have feature xi and I have feature xj. Okay. And Aldous Hoover said that this is a pretty natural model. In particular, any family of random graphs Gn, which come from some infinite graph and which is exchangeable, gives this. Okay, so that is, for dense graphs, this is sort of the natural class of models. Then I introduced some notions of similarity. One of them was just counting subgraphs. So this is essentially counting induced subgraphs. So if these were distinct, then you would just look at k different vertices in your large graph. Then you look whether an edge is there if it's in the graph H, and you look that it's not there if it's not in there. So this would be the indicator function that it's an induced subgraph, and you count. And it's convenient for me to allow these to have conflicts, and I divide by 1 over volume to the k, and the 2 would be the same as n goes to infinity anyhow. Okay. And then we define sampling very similar. We choose x1 up to xk uniformly at random, and we output the sampled subgraph. And they're actually similar in a very precise way. You can just look what is the probability of seeing a particular graph. Well, it's a number of times you see it divided by the number of maps, which is just that. Okay. So as a consequence, if you want to know whether these distributions are similar or these numbers are similar, there's a very simple one-to-one correspondence. The total variation distance between the two distributions is, I'm using a slight abuse of notation to write the total of the random. I mean the total variation distance of these two variables is nothing but 1/2 the L1 distance. Okay. So the two of them are equivalent. So at least two of these notions are equivalent. I introduced two other ones, generalized min cuts, where you had weighted cuts weighted by some matrix J, and alpha fixed the size of the classes. So this generalizes min by section, where J would just be sort of the off diagonal one, and alpha would be 1/2, and there are sort of all other kinds. You can get densest subgraph and all kinds of things are in here, and these are generalizations of that. And the physicists were introduced in the free energies. They were also defined in terms of these cuts, but you weighted things by e to the minus beta, some took the log, and you got your free energy. I will not discuss these much more this time, except that I will state I won't state the main theorem yet, because I also introduced, still review, the cut metric. So what do we do for that? We take our graph, we create a checkboard, and then we put a black dot wherever there is an edge, and a 1, and otherwise a 0. And here I have drawn ones as black and zeros as white. Maybe you want to do it the other way around. I don't know how your computer science encode ones and zeros, but on the screen. But I've done it like that. And so now we defined a cut norm. So in the example where this W would just be some step function like that, okay, here I've drawn an example where S would correspond to a set of vertices, T corresponds to a set of vertices, maybe this, and T is another set. And in this picture, this is S, this is T, and then the red edges are the edges in the graph which go from S to T. So it's a cut between S and T in the graph. And so this would be the cut in the graph. And you do the maximum. So in other words, if you compared two objects, you have a picture like that and a picture like that on 50 vertices. It will look sort of similar like that, and you will compare the cuts in these two graphs, and they will be very similar, and therefore they will be considered near in this norm. Okay, but if I start to scramble, if I relabel the vertices and put all the odd vertices first and then all the even vertices, you would start to get a picture with lots of white and black mixed around. And if you subtract this one from it, you would get something which is very near to 1/2 or 1/3 or whatever you get there, and it will never go to 0. Okay, so this one doesn't have invariance by permutations, which we'll have to fix. But before fixing that, let me note that equivalently, you can write this like this. And the reason is, well, let me do the sort of fancy answer. This is a linear function in F and linear function in G on sort of this compact domain and convex compact domain, whatever. So it will take its maximum on either on the boundary, so on 0 or 1. Or you can just check it. Okay, if you have a contribution here, okay, now if you have a contribution here, okay, and f of x contributes, well, if I make x larger, then the contribution gets larger. And if f of x contributes negatively, well, if I go f down to 0, I make it larger. So in either case, make it 0 or 1 on each point x, and you can only make this guy larger. And so you prove that these are the same. Good. And finally, I defined the cut distance by saying you want to do, now you would like to have invariance under relabeling of vertices. What is relabeling of vertices in the continuum? Well, so this is a vertex x, and phi of x is a relabeling. And what would we mean by relabeling? Well, we want that if this starts off uniform, that phi of x is again uniform, because that would, with analog permutation, do that on your uniform distribution on discrete things. So we ask these to be measure preserving bijection. Then if this is uniform, then this is uniform. And so now we define the cut distance between two graphs by saying we take the cut distance between the step functions, and then insert all of this. So here is your full formula, what the distance between two graphs is. Okay, all this we had done last time. And I had stated that theorem. So you have these different notions, the subgraph frequencies, the distributions. We already know these are equivalent. You have this, you have the microcanonical free energy. And the theorem says that being a Cauchy sequence with respect to this cut matrix is equivalent to all of this. Yes?
So is it meaningful to normalize the cut distance with the volume of S cross T?
So I don't do that. So I divide by 1 over n squared. I mean the dense setting. And it turns out that this cut distance, if you divide by, so let me just go back. Okay, let me just do something. Okay, so this min, here, did I call it multi-min cut? Min cut. So, alpha. Okay, so this was the minimum overall. Let me write it in a different way. Overall partitions, V1, disjoint union, disjoint union. D, size alpha times n, alpha I times n, of sum over I and j. Squared, j I j, 1 over n squared, the number of edges. Okay. So you see in these min cuts, I divide by n squared, not by the size of the groups. And my cut metric similarly divides by n squared and not the size of the groups. Okay, it's a different notion of a cut metric. I mean, for the cut metric, I can define whatever I want. This is my definition. And in that definition, I mean, it's just the right definition. You could define it differently, you would sort of later get a different regularity lemma and stuff. But this is the right version to prove all these equivalences. And the other one is the slightly stronger version because you divide by something small. Okay. Good.
I have a question.
Yes.
For this space, with respect to the time measure, is it always complete or only complete for dense graph?
Only for complex, for dense graphs.
Only complete for dense graph.
So, so the thing is compact for dense graphs, and it's not even pre-compact for spiral. If you have extra conditions, you can make it again complete. Okay, but if you just want all, so anyhow, Jennifer might get to that on Friday. I'm only discussing dense graphs.
I think it's complete. It's just for sparse graph, you're not getting anything interesting.
Oh, if you do it like that, it's complete. Okay, it is complete, but your subsequence may just converge to 0. Okay, yes, you're right. I actually was making my life too complicated. If you divide it by something else, you would still maybe be, then you could discuss whether it's complete or not, and gets complicated. Anyway, so this is the theorem. And the general, I even mentioned that last time, so this will be the end of my review. So the proof idea is prove that if the cut distance is smaller than epsilon, that the other properties differ by at most a constant times epsilon. And it turns out when you actually do it, the constant will be moderate in terms of your other constant of the problem. So it will be k squared times the norm of j typically. In this example, you already can see that this is sort of something like a cut. Okay. And then you sum several of them up. There's sort of some k squared of them up, and there's a j. So here you already see that this min cut on a given, on sort of two graphs, both on n vertices, actually, if this is smaller or equal than epsilon, then this will be smaller than epsilon times the L1 norm of j or the infinity norm of j times k squared. And in general, you have to do some rounding to get sort of to the other. So it's just true. Okay, so you have, so this is typically easy to prove. Okay, the other direction is more difficult. And often we will require actually that the k in the previous theorem is sufficiently large to give you a good enough approximation. So it will often be exponentially large in 1 over epsilon squared, which has to do with the weak Samaretti lemma we'll discuss later today. So I will now want to give you the proof in terms of the subgraph sequences and the cut metric. Okay. And I do the easier direction first. Okay, so this now, today I will give you a few proofs. So, so I have 3 proofs. So, and I have 3 times half an hour. I've used up a little bit, but so how would we try to prove that? Well, remember that this cut distance was defined in terms of empirical graphons. So it makes sense we want to have these empirical graphons appear, okay? So look at this, okay, and define this T0, the subgraph frequency of a graphon by this formula, just a formula, okay? You integrate over x1 up to xk if you have k vertices, and then you put a w for the edges in H, and you put a 1 minus w for the edges not in H. And now I claim this is equal to that. And in a paper, I would say by inspection. So I inspect that a little. Okay, so how does the inspection go? Well, let's look at one of these little squares. Okay, so if we have here a fixed graph G, okay, here is G, then on these little squares, the function is constant and equal to the adjacency matrix. That's how it was defined. So if I integrate over this square, well, in general, so that means all these xi's, I always have to only keep track which intervals they're in. So if I integrate over these k intervals, I get a factor n to the minus k. Now I have fixed the intervals. So now if a sum over vertices in your graph, this becomes the adjacency matrix. You have here 1 over n to the k. And now if you remember the definition of this thing, it was just, I don't know if it makes sense, I should do that. Here you have it, that's exactly this. Okay. So that we have, okay, that's step 1. So now we have gone from graphs to graphons. So now we want to prove this thing for difference of graphons. Okay, so you do that in 2 steps. First, you observe that if you take your graphon and replace it by one where you relabel vertices with a measure preserving transformation, that this doesn't change this object. Second, you will prove a bound with this cut norm, not the cut metric, for this difference. So assume we had both. Well, so this difference is equal to the difference where you put the graphs G, which is equal now if I replace here WG by WG phi, this is equal. And then I use this bound, so I get this. Okay. And now I take the infimum over all phi. Then I get this, which was, and I forgot the factor k choose 2. So if I copy down this factor k choose 2, then I have proven one direction. Okay, so it's a super easy proof. Okay, well, it's not a super easy proof because I have still to do step 2 and 3. Okay, so how is step 2? This is again one of these proofs by inspection. Okay. So let's inspect it again. Okay, so if I replace this W by W phi, what does that mean? Everywhere in here, instead of xi, I have phi of xi. This integral is just an expectation with respect to k independent uniforms. And if xi's are uniform, then phi of xi's are uniform. That was your definition of a measure preserving transformation. So this is still an expectation over k independent uniforms. So you get this. Okay, so this is just how measure preserving. And so that step is also easy. So the last step is actually the only place where it requires some work. Okay. So let's do that slowly. Okay, so we have, I write this thing, we have this subgraph sequences of W. Okay, so we write this out. And now since I don't want to sort of have these funny things, I just define Wi equals this or 1 minus this. So it's just the product over I smaller than j of some functions. Okay. So now then this is obviously this. So how would we bound this difference? Well, iteratively. I will first replace W12 by U12. Then I will replace W13 by U13 and so on. So I will have n choose 2 steps. Okay, and in each step, I get a difference of the one I'm just moving. And here I get a product of the W's for those I haven't moved yet, and for the U's I have moved, which is again some function. Okay, so in each step I have this, and I have, if you want, in front those I haven't moved yet, and in the back those I have moved, and for those I haven't moved I still have a W, and for the other ones I have a U. And if you want a more formal proof, it's a telescoping sum difference, which is sort of a more fancy way, but I think this is actually more intuitive.
Sorry, what was U then? U was the...
Yeah. So you had, I wanted to compare T0 of H and W and T0 of H and U. Right? I want the difference of this here. So the Wij's are these, the Uij's are U or 1 minus U, depending on whether this is the case. Okay, and now when I want to look at this difference, I can say, okay, I have to move all my Wi's to Uij's. So I have to move the first one, the second one, and the third one. So I can write this difference as one where I have not moved any, where I have moved 1, where I have moved 2, where I have moved 3. And if I subtract them each time, you get sort of this difference. And so you get this difference, which is sort of the step where we are moving the edge ij, and some of them have been moved, and they're already the u's, which are either u or 1 minus u, or there's the w's, which are either w or 1 minus w. Okay. So we need to estimate integrals of this form, okay, where this is either this or this. But we will not. So now let's observe the following, which is super important. Okay, these guys will depend on maybe xi or maybe xj or maybe neither, but they will not depend on both, because we had to sum over I smaller than a product over I smaller than j, and this is the term which has the edge ij. All other edges are different edges. So in particular, they don't contain the pair xi, xj. So if you think of this as a function, so if you look at this whole integrand and you look at these as a function of xi and xj, these guys will only depend on one of the two. Okay. So imagine for a moment when we estimate that, conditioned on all the xl's which are not equal to I and j. What do we get? Well, we get a wi that we get this factor. This certainly depends on I and j. You get a product of some of these guys which depend on I, which I collect in f. You get a product of some of them which depend on j, which is in j. You get the product of the others, which I throw also into g. And now all of these were u's or 1 minus u's or w's or 1 minus w's. They're all between 0 and 1. So in other words, f and g are functions with values in 0 or 1, which obviously implicitly depend on all these other xi's, which I have fixed. But it's a function of xi and xj. You can factor this dependence out. But I observed that the definition of the cut norm, if I take the absolute value here and it takes the supremum over all functions f and g, I get the cut norm. So in other words, the absolute value of this integral is bounded by this, okay, uniformly in the remaining other variables. So now if I integrate over the other variables in 0, 1, I just get 1. I get nk choose 2 terms. So I get that this is bounded by, and each time you have the same bound here. Here's the integral over the other variables. This gives 1, this gives j, so this gets z, which was our last step.
Maybe I'm missing something. Simple than the previous slide. Why can't you just upper bound it by 1 and then
Come with F and G, you know, correlate.
So that would be, maybe one should first sort of look at that way, okay? So if I look at this object here, okay, and I take this difference, okay, what you could say if I just want to look at, when I sort of look at this object, right? Just bound this by 1. Then you get the integral of that. Bound that, since you have thrown in absolute value, you have to throw in absolute value here. So you get the L1 norm. So the lemma, so the first step, so the step 3 in the L1 norm is sort of trivial. Okay, but you want the cut norm. The L1 norm is too strong. So to get the cut norm, you have to do this trick. Okay, so you really need to do this F and G trick here to get out the cut norm. By the way, in this case, I don't even need the equivalence because the F's are all coming from adjacency matrices. So actually the F and G's are all 0 or 1. So this is actually the original definition of the cut metric. But now I have proven for you this bound for general graphons and not just for step functions. Okay, so that is one direction. So now, what if we want a bound in the other direction? Okay, so here's a theorem. And the 10 and the 20 are not optimal, and actually that's not what we get, but that's a sort of the nearest nicest numbers. I didn't want to have square roots of something in the NC. That's a the difference is smaller than 19 or 18.5 or something. But I mean, you get something like that, and sort of from the, I will indicate to you why it's sort of not avoidable from the proof. So maybe you need a 2 or so, well, anyhow. So anyhow, if we have a k such that the total variation distance is bounded by 10 over square root of log 2k, then I claim that the cut distance between your two graphs can't be much larger. Okay, so why is that? Well, what we will do is, how will we prove that? We will look at this guy, but I will do a triangle inequality, and I will bound this guy by the difference between G and a random graph, GK of W or of G. Then I will take the difference between two of those, and then I will take a difference of the last one. And in this triangle inequality, this guy actually goes to 0. So let's look at this statement. This statement says that if you choose an inhomogeneous random graph generated from a graphon, it converges back to the graphon. Now you may have, some of you may have seen that for G and P. Okay, if you calculate cuts in G and P, okay, you want cuts between S and T. Well, in expectation, it's just S times T times P, which P is this random variable. There are n squared many random variables, so it's super highly concentrated, exponentially in n squared. There are 4 to the n many possible S and T's, so it's still highly concentrated. So it's so highly concentrated that you can actually converge this expectation bound to a bound sort of which goes with, yes?
Just a quick, GK and K are the same. GK of W and the thing you have.
They are the same. So this is what I'm saying for all graphons. I will use eventually that this and this is the same. And that is actually why I defined this guy the way I defined it, because otherwise I wouldn't use this. Okay, I will comment on that on the next slide. But okay, so it's not hard to show that this fits. Okay, so this GNP argument holds for W random graphs as well, except that now you also have to compare the matrix W of xi, xj to W itself. And so there's an extra step where this can be either proved by some abstract nonsense. For those who you know, it's called U statistics. And but you can also prove it really by hand in this case. It's sort of, I gave that as an exercise in my upper division undergrad class. Okay, it's easy to prove. Nobody complained about that exercise. It's really easy to prove. If I give you the hints how to prove it, he can prove it in half an hour, because he's done this stuff a lot, and anybody in the audience can prove it in an hour, and my students need an afternoon. Okay. So that's easy. However, in general, the bound you get, the rate of convergence, is just abstract. We know there is some rate of convergence. It's U statistics. And in particular, it will depend on W. So that will not be good enough if we want really this quantitative bound. It would be enough to prove that convergence of these samples for all k imply this being a Cauchy sequence, but I wouldn't get any explicit bounds. If I want explicit bound, I need a little more. And for that, I have the following quantitative result on the expectation. Okay, so it says then in expectation, this object is bounded by 5 over square root of log 2k. Now, this result is one of the central theorems in this paper of 50 pages, and it relies on 2 things. One is, when you want to calculate the cut norm, you can again use sampling. So you want to calculate the cut norm between, let's say you want to compare GK of W and GK of some other U prime. That means you take sampling on your W or on a graph. And there's theorems that if you want to calculate a cut, you can calculate it in polynomial time sampling with some. So there's some FP test to calculate that. that wouldn't get you such bad a bond, okay? But it turns out that you also at some point in this proof need to go to a stochastic block model. So your proof will actually, in the technical details, at some point, not in the sampling, require to use the stochastic block model. So you will have to approximate W by a stochastic block model. And for that, you need the regularity lemma. And luckily, you only need the weak regularity lemma for you don't get a tower, but you get something like an exponential, which in this version is the inverse function of it. So you get this bound. Okay. So I will not prove that to you. It would probably take half an hour if I sort of already have proved the Samaretti lemma and if I had the sampling lemma. So anyhow, it's true, okay? And so we will use that, okay? But I argued to you that it should converge, okay? Now it's actually easy. So let's look at that. Okay, now this is just Cauchy-Schwarz, right? I take this W, I do the graph sampled from the GK of the graph. Okay, so this is just, I use this as an inhomogeneous random graph. So I have here now my two inhomogeneous random graphs and I have this. Now I take expectations and use the previous bound. So the previous bound said this expectation was smaller than 5 over square root of log 2k, uniform in W. So it holds for this one and for this one. So it's just 10 over square root 2 log k. And this one is the expectation of these two guys. And in principle, I have a distribution here and a distribution here. And I can choose them independently of each other. I could choose it the same. I can choose any coupling, okay? So now if I can choose any coupling, okay, so it's still true here, okay? So what do I do here? This is a number which is between 0 and 1. So the expectation is bounded by the probability that it's different from 0. And now if I use a general coupling between these two randomness, this is actually nothing but, oh, I haven't done the coupling yet. So now I claim this. Why do I claim this? Well, I claim this is equal to this because this guy has the same distribution as this. So why is that? Here I choose x1 up to xn, x1 up to xk, uniform at random in 0, 1. With probability 1 over k, that will fall into an interval corresponding to a given vertex here. So in other words, this sampling I effectively do by independently choosing x1 up to xk in 0, 1 correspond to choosing v1 up to vk independently in your vertex set. But that was the definition of sampling. So that answers your question, Yegane. And it also now tells you why I did sampling with repetition. Because this guy, for this continuous variables, there's no way to have not repetition. I mean, they don't repeat anyhow, but anyhow. So this one translates to that one and not the one without replacement. So this is equal. And now this probability, okay, if I do a coupling, is bounded by the total variation distance of the two samples, and which our assumptions of the lemma said that we assume that this is bounded by this.
Christian, indeed, this assumption is indeed because of your lemma coming from the other thing, right? If can you click the next one? If this expectation was not of order 1 over reciprocal of the square root of
No, that is bracket.
You should have.
Okay, if I had an epsilon here,
yeah, then
this would be 10 over this plus 2
epsilon.
epsilon.
Exactly. The crucial.
So I put this bound here because I have a bound like that anyhow. Right? So if I put here 1 over log 2k, then I get here 11.
Yeah. That's what I'm saying. So this is essential, but you are not going to show us that, right? Expectations.
So, and this log 2 comes from the Samaretti, which I will show. Okay. So it sort of makes some sense. Okay, why does it make sense? If you look at a sample from a large graph G and k vertices, that sample will produce you a graph on k vertices. Okay, so this will actually produce to you, for those of you who know Samaradi partitions, it will produce you a Samaradi partition where our probabilities are either 0 or 1. Okay, so this sampling actually produces a block model approximation to your graph morally, right? So I have this graph, I sample, and now I get back another graph. Well, this graph is sort of some approximation to my original graph. And there is a theorem, which is sort of, I'm certainly not going to prove, that if you want that this is distance between a graph and its sample is smaller than epsilon, you need e to a constant divided by epsilon squared. There are sort of counterexamples which will actually work through the proof I'm going to give you later. And in each step, change your graph in such a way the bounds I'm proven will be tight, and prove that the bound I will prove will be actually up to constant optimal. So you actually need something like that. Okay, so this is not an accident. You really need, you can't expect to just sample 4 vertices from a large graph and get a good approximation. So you can't expect this to be polynomial for general graphs. I don't know whether, so you can't expect it, and I would almost think that using the results we know about Samaradi partitions, you could actually prove that you can't do it. Anyhow, you can't.
Detailed question, perhaps this existential K. How large this K is should be in order to.
No.
How do you see the existential K sampling? There exists a K such that blah blah blah.
So if K is, I don't know, 2 to the 100 over K squared over. So it has to be large enough that this is smaller or equal than 1, or if you want smaller than 1/2. Otherwise, so if it's not smaller than 1/2, this bound is trivial. And if this is smaller than 1/2, you're fine. And if you want to be 1/10, then you get sort of, so you get sort of, if this should be epsilon, you get something that's exponentially 1 over epsilon squared. So that was an easy technical question. I can probably explain that to my first students. So summary so far. Graphons are functions of 2 variables in some feature space. If you give me a probability distribution over features, I get a natural random graph model called inhomogeneous random graph. Suvik mentioned this morning, you can make us also sparse by taking this graph and then keeping each edge with probability 1 over n. Now suddenly you get a sparse graph. So that is the inhomogeneous random graph in the sparse regime, which was first studied by Bolabas, Janssen, and these guys. And then we proved the theorem, which Suvik mentioned. Okay, and finally, if 2 graphs are close in the cut metric, they have similar subgraph counts, distribution of sampled subgraphs, multi-way cuts, and physics quantities, free energies, and you can turn it around. And I showed you how to turn it around in the case of these 2, which we have seen are equivalent. And I hid a little bit from you how to exactly do it, but I also hinted to you how you could do it extensionally if you only can prove that these. So what have we seen? We have seen that graphs, so no, that we have not yet seen. So we have seen that if you take a graphon, you get a graph, and for any n, you can generate one. And we actually have seen that this graph gives back the graphon. We have not seen that in general how we have a sequence of graphs convergent, but we have seen how the graphs you generate like that converge back to Z. Okay, and if you just want that for a given W, it converges at some rate you have no understanding of, that's easy to prove, and that would already give the equivalence on the previous side, but it wouldn't give an explicit bound. You could worry that it's a tower of towers or an inverse log star or who knows what, okay? But it's not that bad, it's only exponential. Okay, so now I want to discuss limits. Okay, so I want to discuss graphon as limits in the cut metric. And heuristically, it's super easy, okay? So we already have seen that any graph can be embedded into the unit square. And now here, and I hinted that, but I didn't draw that picture. If now you send n to infinity, clearly goes to that picture, okay? If you look at Erdős-Renyi graph, it looks like that. And if you squint your eyes a little bit, you don't see it here, but this is actually gray. And it's
the side projection. Christian, look at the other side.
Oh, there you see it. Okay, so it's gray with pixel density 1/2. Okay. Now, what does well? Okay, and finally, you can take, for example, a randomly uniform. So, what is this object? You have already grown the graph up to n vertices. You add a new vertex, and then you uniformly again add sort of edges between vertices which are not yet connected. And you do that over and over again. That generates a dense random graph. It generates a so-called randomly grown uniform attachment graph. There's an analog of a densely grown preferential attachment graph. And you get sort of this black and white pictures, and they clearly converge to that. Okay. Now, clearly converge is a question what that means. Okay. So we need some metric. And you might say, well, I do the L1 metric. Well, that will not work very well. Okay, here's the L1 distance between this and this is 1/2 at every point. So this will not converge to the distance will not be 0 in the L1 distance. And here it happens to work, but in most cases, L1 is not good enough. So you might want to do some weak convergence or so, but the right notion is the cut norm. And we already defined that, right? So we will say it converges if and only if the step graphon converges to W in this cut metric where you do the infim over measure preserving transformations. So it turns out that the theorem I just showed you and for which I proved to you the first part, the proofs can be easily generalized to prove this, okay? So if you have convergence in this cut metric, well, I already bounded this for you, which instead of G, I have two graphs W. Okay, so I actually showed to you that this is smaller or equal than this. The same proofs gives that. Okay, the proof in the other way also, again, you put your triangle inequality, the same proof will give it goes the other way around. And these I haven't shown you anyhow, but the proofs you do for those actually will give this sort of for free. Okay, so this theorem is sort of nice. Okay, so you have a limit, and all of these can be expressed in terms of the limit. Okay, so, and you can imagine what happens, right? You will get here an integral over W. So you define cuts in terms of W, you don't divide by N, you integrate between VI and VJ, and VI and VJ are subsets of V, and now you get measurable subsets, and you take the minimum, and that will give you this limit. And the statistical physics is a little bit more complicated, and I will not write it out for you, but you can also write it in terms of the W. So, questions so far? Because now I'm heading towards the Samaredi lemma, but before I do that, I wanted to see whether you have questions so far. Yes?
So for the dense Erdős-Renyi graph, like it's convergence to the half limit that like one can check it in like the cut norm rather than the cut metric.
Okay, so that is actually true in that case in the cut norm, because if you have measure preserving transformations, G and phi minus W, okay, that's the same since they're invertible as W Gn minus W phi. And this is a constant function P, so it stays a constant function P if you don't put the phi. So now you get this in the cut. Right? And now if you want to prove that, you just take the supremum, and then if you write this down in the cut norm, this will be actually the maximum. This will be 1 over n squared, the maximum over all set S and T subset V of Gn of some I in S, J in T. The indicator of the adjacency matrix minus P. This has expectation 0. So in expectation, this is 0. These are n squared random variables which are independent. They're super highly concentrated. You can prove concentration. And so for the random graph, I essentially prove to you that it converges to that. And for the random graph, all the other ones are very easy to control too and see that this is the same. That's sort of a good little exercise to check that it actually works for this. Okay, and for the random graphs, the statistical physics gives what's known as the Curie-Weiss model for those who know what statistical physics is. So in the limit, you get some variational. I mean, here you just get a minimum of the energies expressed in terms of the graphon. If you want to do the partition function, you also have to worry about entropy, and you will have subtract some entropy term and then minimize again, and it will work. Okay, I will not do it for you here, but you can actually rewrite all of them in terms of W.
Like the typo, it's sample K from G compared to sample K.
But sampled K from W is the same as an inhomogeneous random graph on K vertices.
Notation for that.
I had oh, this should be. I see what you're saying. I should put a G here. G, you're totally right. Okay, correct. Okay, so this converges to the inhomogeneous random graph generated by W. More questions? Okay, so we have sort of now completed this picture. Okay, so we have seen that if you form convergence in the cut metric, you have sort of a notion of convergence here. It's equivalent in the cut metric or in all the other ones. And you can choose sort of a random graph like that. And then I told you that it's easy to prove it converges back in the cut metric. And since all of them are equivalent, it converges back in terms of all the other ones. And Jennifer will talk a little bit how to do this cycle for sparse graphs. And if I give you a small sample or not so small sample, a large sample, can I estimate my W? Okay, so that's a little preview on what Jennifer will do. So we have done all that. Okay, so now is, yeah?
Can you say a little bit about the uniqueness of the graphon?
Okay, I can say something about that. Okay, so since here you have measure preserving transformations, it's clear that the limit, okay, so W limit, if and only if delta cut of W is a limit and U is also a limit. If and only if this is 0, right? Because if this is 0, then you could put U there, it would still be true. And if this is non-zero, well, it can't converge to both. Now the question now is, and that also means that these two will generate the same inhomogeneous random graph, right? So that's a question we never asked before, but you could ask, when do two graphons generate the same random graph? And one way is clearly the case. If I look at W phi, right, of X and Y, this is W of phi of X, phi of Y. So if phi is measure preserving even from one probability space to another, then if this is distributed, right, if X is distributed to mu in some space omega 1, and phi of X is measure preserving from phi goes from omega 1 to omega 2, and it's measure preserving, then phi of x is according to distribution according to mu2. So if there exists such a thing, then this one will generate the same random graph, right? So that is what I was mentioning before. You could have some measure preserving transformation from RD with the Gaussian into 0, 1, and this would generate the same distribution if you just transform your graph on accordingly. Now, if you stay in your original space, that's still true if phi is measure preserving. So you might think that this is if and only if. Let's say now both u and w go from 0 1 square to 1. Okay, you might suspect that this is if and only if u equals w phi. Okay, and that is actually what people thought for a long time. One of my colleagues here in Stats had a theorem stating that, but it's not true. Okay. It's almost true. What is true is that if you can find a sequence of doing this operation, it actually turns out the sequence only has to be of length 2. So it's clear that if I have, right, if I have w1 equals u phi 1, and then I have w2 equals u phi 2, the cut distance between this is 0, the cut distance between this is 0, therefore the cut distance between this and this is 0. Okay, and that's a theorem. So w1 and w2 have the same limit, can both describe the limit if and only if there's a third graphon such you can apply a measure preserving transformation to it and get w1 or w2. And that holds in very general measure spaces. You could also put the phi on the other side. It's also an equivalent characterization which only holds over an atomless probability space. Okay. Has to do, I mean, all of that has to do effectively with the fact that if I take this probability space and this probability space, there's no measure preserving bijection between the two of them. But you can map all of them to 6 vertices. And then if you put the step functions in and do this right, this will produce the counterexamples you need, where you really have to go through that to get to see that things like that.
But there's not, that doesn't appear to be a way to think of a best kind of graphon, like a minimal or coarsest graphon to describe the
No, there is actually, okay. There's a notion of a twin-free graphon. Okay, so what are twins? You and I are twins if we see exactly the same graph. So in other words, if w of x and y is equal to w of x, z and y for all y, then x and z are twins. If a graph, and there is, so and if there are twins, you could just collapse the twins, create a smaller probability space and an equivalent description. And that is sort of the minimal description. Okay. And once you collect the twins, you can actually prove that you can map that always to a union of discrete space and a continuous space. So there is, if you want some natural stochastic block model part of the graphon, plus some continuous part, and there is some very precise notion in which it's minimal. Namely that of contracting twins. When you contract twins, you will get a few atoms. They will give you stochastic block models. And there's some part which is not contracted or which sort of just gives you back intervals. And those have to still be described by a continuous graph. So this, I mean, to prove all of that requires quite a bit of measure theory, because you can imagine, I mean, this is effectively, if I change things on a set of measure zeros, that generates the same thing. But now you get countable, or maybe if you do these twins, you already have uncountably many. I mean, the twins, I mean, it's sort of, then you need to talk about measure preserving partitions of probability space. It's sort of, it gets sort of complicated, but you can do it. Okay, so now let's go to another question here. So the uniqueness question is an important question, and if I sort of thank you for asking this question, maybe I should have put it on a slide, but I didn't want to. So this is sort of what we know about uniqueness. Now, given that I defined this, okay, there are two questions, okay? So I have this equivalence, but if I just had stated the theorem and you hadn't seen what I did before, you might say, well, any step function, if I make just if I make Gn just as graph on 3 vertices and keep that graph, then it will converge to its own step function. So there clearly exist limits. But do there exist non-trivial limits, right? Do there exist graphs on growing sequences which are not just taking a stochastic, taking a finite graph and just blowing it up such that it looks as, I mean, I can always take a vertex, divide it into 3, put a complete graph on it, and sort of create some trivial, but are there non-trivial examples? Okay. And then can we get an arbitrary graphon as a limit of a sequence of graphs? That's sort of a little bit more than that. Okay. And finally, given a sequence, is there a subsequence that converges to a graphon? Okay. Now, the answer to the first two questions I already gave you, because I said that my students can prove that in the cut matrix, this converges to W for every W. So this is non-empty, and actually I can get any graph. Okay. And now this one, well, the answer is also yes. Okay. So it turns out that every sequence has a convergent subsequence. That means in particular, every Cauchy sequence converges. So for those of you who think topology, that means that the space of graphon, if I identify those which have cut distance 0, becomes a compact metric space. Okay, so with these two yeses, what this shows is that the space of graphons is the completion of the space of finite graphs in the cut metric if I identify graphons which have 0 cut distance. Okay. So if you want, I don't know, G is a set of finite graphs. If I take G and identify things with respect to the cut metric and put the completion, then this is just the set of all W. One, again, identifying object by the cut metric. So this is sort of really, so the complete graph theory is super nice. And so this will, for example, this would not hold if I allowed weighted graphs or multigraphs, because then you could put arbitrary weights on your edges, and then clearly W would become unbounded, and then clearly you could produce a sequence which goes to infinity and doesn't have a limit. Okay, so this shows you already that if you start to have unbounded graphons which should describe things like power laws, things will go wrong somewhere. So now I will spend the rest for you to actually discuss the answer to 3. Okay, so there is a weak regular terminal which says the following: given any graphon and any k, there exists a k times k matrix B such that W can be approximated by the step function which is constant of intervals of length 1 over k and takes the values of your matrix B. And so put differently, any graphon can be approximated by a stochastic block model. Okay. Or you could also read this differently, since convergent in this is sort of again related to the convergence of the random model generated from that to the other one. So what does this, for example, tell you? If I have any graphon and I generate an inhomogeneous random graph. So we know, okay, you have any graph which is exchangeable. You know there must be a graphon generating it by Aldous Hoover. Now you use this lemma. So you know that that graphon can be approximated in the cut metric by a block graphon. Okay. And now since converge, and it's near, and since convergence, the cut metric is equivalent to convergence in subgraph counts, for example, this tells you that the subgraph counts in the stochastic block model will be similar to those generated by W. So if you only care about motifs in the language of social scientists, and you are not worried about approximation by some epsilon, there's no reason to consider a general graph. In the dense setting, you can always approximate it by a stochastic block model. And if you're a physicist and want to discuss physics, the same is true. Okay. So, and if you're computer science and want to have sort of max cut and min cut and things like that, the same is again true. Okay. So that is that. Okay. Second, why is that true? So I claim this means you can actually cover this set of graphons by some net of block graphons. And for each epsilon, it's finite. Why is that? Well, for each epsilon, okay, I can choose a block model, which is distance epsilon over 2. And now the block models, it's just a compact space. If you fix K, it's just, okay, you can just choose the numbers between 0 and 1, and you sort of just make them sort of, you take discrete values. I don't know, 1 over K is probably good enough. And then they are sort of smaller than 1 over K away. So your epsilon half became an epsilon. So you get an epsilon net. This is what's called, sometimes it's called pre-compact or so-and-so bounded. What's the name? Essentially bounded. Totally bounded. So this shows that your space is totally bounded. That doesn't give you yet subgraph convergence. But with some extra work, actually, you can get subgraph convergence. Okay. So I will want to convince you that this is true. And so that I will do on the board.
Is the 5 in the numerator the actual number, or is it
No.
something else?
Okay, you will see how the 5 comes. I will first move to something where this is square root of 2. Okay. And then, but I will have to, the square root of 2 would say there is a block graphon with not necessary constant block size. So the way I had defined stochastic block models, they had the same block size. If you didn't want the same block size, then actually I could have here square root of 2. Okay, that will be actually the lemma I'm now stating. Okay. So epsilon, and for all, I need a definition. Okay, so a partition of 0, 1. So I have some collection of subsets. If 0, 1 is a disjoint union of these, this is called a partition. Okay. And the way we will produce this object is we will take actually average W over blocks. So what is W of P? So that's the average. Okay. So that will be constant on yi cos yj. And what will this constant be? It will just be the average of the original graphon over that block. Okay, so this will be equal to 1 over the Lebesgue measure, which I just write as yi times yj. So that's, these are arbitrary sets. So this, you should write the Lebesgue measure, but I will use that notation for the back measure times the integral over yi cross yj of w of x and y. Okay. And then there is a lemma, which is actually in exactly of this form, 2 to 3 can, 9, something like that. Question mark, okay. It's 2 to 3 can, and it says that for all epsilon larger than 0, for all graphons W metric, exist a partition P into at most 4 to 1 over epsilon squared classes, such that W minus WP in the cut norm is smaller or equal than epsilon. Okay. Now, this is depending on the graphon. I get different partitions. Okay. But I never need more than many classes. Now, when you write this here, this BW would actually have a partition into intervals, right? Into adjacent intervals. Here this lemma only gives sets Y. So how do I get from sets Y to intervals? I apply a measure preserving transformation. So then these guys actually become intervals of this length because it's measure preserving. So that, and if I apply a measure preserving transformation, that doesn't change the cut metric. So if this was smaller in the cut norm, after the transformation is still smaller in the cut metric. Okay. So, and now this 4, if you take the log, this would be sort of, right, you get log base 2, so you would get here square root of 2 over log base 2 of k. Okay. Now, this actually says they exist, so what if k is much smaller? Well, you take your plot model and artificially divide it into smaller blocks and choose for W the same on it. Then this hasn't changed anything. Well, I'm cheating a little because on your smaller subblocks, this would not be the average anymore. So you need to repair that somehow. So that will cost you some factors. But if you do that, and I have sort of a division into 5 intervals, one is this length, one is this length, one is this length, I can subdivide into tiny intervals. Now, here's the end of that. So I have a division into 3 intervals. Okay. So this will be my k, which is smaller than. No, it's 3 intervals, but they don't have equal lengths. Okay. So they look like that. Okay, so that will be k smaller than 4 to 1 over epsilon squared. Now I take a very fine partition. Okay, and I replace my graphon by the one that I just claim it lives on this partition, but I don't change it. Okay. Well, so it all works out very fine, except at this boundary, because I don't know whether I choose this or this. So I make an error here, and I make an error here, and I make an error here. So the total error I make if these are Q classes will be 2k over Q, because you have sort of a square and you have sort of your errors here and here and here. Okay, so you make an error here. So you have to make Q large enough to control this error. So you want that to maybe be epsilon over 2. So now I need to have epsilon over 2, so suddenly I get here a 4. And actually in my proof, I will need epsilon over 3, so I actually get 9. So I'll already get 2 to the 18 over epsilon squared, okay? So I will make my original error epsilon over 3, then do this subdivision into enough classes that this error is small, and then I have to do some other massage where I will lose a little bit more. But this is already 18, okay? And 18 is bigger than 4 squared. So if I don't want to write here 4 point something, I'm forced to put a 5 here. Okay. And so you see where this comes about. And sort of, this is not, nobody says this is optimal, but anyhow, so we want to prove this lemma. Okay, so I argued for you. I didn't quite control the errors here, but you believe me that this is sort of just this little rounding errors at the boundary that any of you can do that and write it out and you will get some bound. Okay, you have this error which you have to control, you have to account this error, and okay, so we have to prove this lemma. So how will we prove this lemma? We will use some function, some cost function, which will start below 1 and will go down all the time. And we know, and each time I've come up with better and better approximations. And this cost function, I will define it such a way that it's non-negative. And then eventually it will go down below 0, at which point my algorithm has finished and will have produced a thing. So how does that go? Okay. So what I will do is I have the following algorithm. I define a partition P0, which is just it's a trivial partition. Okay. So WP0 is just the integral of W, the constant function. Okay. And I will refine 0, P1, and so on until cut distance between W minus WP. PT is smaller or equal than epsilon. Okay, so this will be my goal. I will construct such a thing that it will finish latest at some time t. Okay, and okay. So and okay, or PT goes up by at most a factor of 4 in each step.
This is finer and finer partition.
So you do finer and finer partitions. Okay. And each time, so how will that go? Okay. So let's assume by contradiction that W minus W PK, I call that K, so I really shouldn't call that K. PT in the cut norm is bigger than epsilon. Okay, so my algorithm hasn't stopped yet. Okay. So my starting partition is just the partition into one set, which is the whole interval.
So like you are defining, what's the third line?
Define P0, P1 until this condition is a cut norm. Until this is smaller than epsilon. And I claim that the algorithm will finish at a time smaller than 1 over epsilon squared. But let's just do it instead of claim, and I don't do any of this. So let's assume this is bigger than epsilon. That means there exists an S and T such that the integral over S cross T of W minus WPT in absolute value is bigger than epsilon, right? That's just definition of the cut. Okay. So I write that as the scalar product of the function W and 1S cross T. This is bigger than epsilon. W minus, sorry. T is bigger than epsilon. Okay. So if this is bigger than epsilon, here is the vector W minus WPT. And then if the cut norm is bigger epsilon, there must be this vector here such that the scalar product is sort of something non-zero. Okay. And now morally, I just subtract that from this guy. And I will keep doing it, and I produce things which get nearer and nearer to zero, and eventually will have distance epsilon. That's a geometric picture, but how will it work? Okay, so this is bigger than epsilon, and now I define, this is too low. So I define pk plus 1 as a common refinement of the partition pk, the partition t and t complement, and the partition s and s complement. Okay, so you have some partition into groups. Okay. Let's say I only did with T. Okay, so somewhere is my set T. That goes up to here. Well, then I will sort of divide here. And this is T complement. So if I just, I had just, in this case, I just have divided one class into two. Okay, but if this set is not as well aligned, if this set would sit here and here and here, then you could sort of, in principle, you can get double as many classes, but not more. And if you do it for this guy, you could also get double as many classes. So we know that pk plus 1 actually is smaller or equal than 4 pk. Okay, so the number of classes goes up by at most a factor of 4. Okay. And now, let's observe something. If I look at the integral over s cross t of wpk plus 1, well, since s and t are sort of subclasses of this, okay, this is just the integral over s cross t of w. Okay, so therefore, so that is one observation. And now let me just take my notes so that I do it most efficiently. So now we have epsilon is smaller than integral s cross t w. Okay. So it was w, but now I write wpk plus 1 minus wpk. That was just this assumption, right? Because I now wrote the w like that. So that's my assumption. Okay. By Cauchy-Schwarz, this is bounded by the 2 norm of 1 s cross t and the 2 norm of this guy. So which is the 2 norm of w pk plus 1 minus w pk. And this is bounded by 1, so I get rid of it. And so now here, okay, so now I have that epsilon squared is smaller than integral wpk plus 1 minus wpk squared, which is equal to what? Wpk plus 1 squared minus 2 integral wpk wp. Can you see down here? Wpk plus 1 plus wpk. But this one, again, because we're refining here, you actually can replace this by just, right, this is the same as W. This is, if you look at this here, this is refined, but then I integrate of it. So by effectively, I average over these blocks anyhow. So this is equal to that. So in other words, I have shown that we now have, okay, so I've shown that then we have W as at epsilon squared smaller than W pk plus 1, 2 norm squared, here comes the pk plus 1 squared minus W pk 2 norm squared. Okay, so now I get that WPK plus 1 squared is bigger than epsilon squared plus W K squared. And now I iterate, so this is bigger than. Can you still see up to here or not? So this is bigger or equal than K plus 1 times epsilon squared times plus W 0, which was just W, which I just bound below from 0. Okay. But this guy is a function between 0 and 1. I average it, it's still a function between 0 and 1. So this is bounded by 1. So now I have said 1 is bigger or equal K plus 1 epsilon squared, which means that I can choose that actually I will never have to do the last step. So latest as step K, I will have violated this condition. So latest at step K, I found a partition so that the cut norm is smaller than epsilon. And since in each step I only go up by a factor of 4, I get this lemma, which is not here anymore. So I get that the number of classes. So the proof gives the number of refinements smaller equal 1 over epsilon squared, and the number of classes smaller equal 4 to the 1 over epsilon squared. Okay. And note that this thing is actually polynomial. So if I could do this step constructively, which we currently can't because I have to still look over all S and T. But if I could do this step constructively, I would have given you a polynomial time algorithm to find an approximation into exponentially many classes. Okay. And Fries and Kahn actually pushed that a little further and approximated this step. And I mean, morally, okay, they didn't quite find exactly the right SMT, but they're essentially proved in each step they had a W, and in each step they subtracted a rank 1 object, and they went on and on and on, and they eventually approximated an arbitrary matrix by a rank 1 over epsilon squared matrix at the cost of an error order 1 over epsilon squared, or maybe it was a different polynomial. So this can actually be made into something constructive. And it's one of these funny things where I have an object which is exponentially large, but I have sort of a finite description. I mean, it's always polynomial in n because I have to write down your vectors. But you can write down, so their theorem eventually says if you have any matrix with entries in 0, 1, you can find the block mode matrix, and you can write it. There is some effective description which is polynomial in n and 1 over epsilon, which gives you this approximation. Okay, even though the number of partitions is exponential. So, and the fact that you actually need exponentially many partitions, what people do, they give you a graph, so they give you a graph, and they iteratively, they make it such that on a large scale, the best thing you can do is this. And then on the next scale, they refine it, make it such the best thing you can do is that, and so on. And they show that on each scale, you are forced to sort of do essentially what I'm doing here in the proof. And they show that you need e to a constant over epsilon squared many classes. Okay, so this bound is actually optimal if you don't care about the constant. And with that, I think I have given you, I think this is one of the most beautiful proofs I ever, I always was scared of Samarati lemma. And then when I saw this Fries-Kahn proof, I thought, oh, this is one of the most beautiful proofs I've seen in the world. I mean, and it's sort of also almost like, I mean, I don't know, didn't you show one proof where you had a, what do you call it, potential function? So effectively, this is a potential function, right? So you have this potential function, you show that it sort of must go up and up and up, and it's bounded by 1, so eventually you're done. Yeah.
It's probably a way to break the martingale convergence. Because the proof of the martingale convergence theorem looks somewhat like that. Is a backward martingale condition on defined filtration. In this case, filtrations are partitions.
But here you enter a finite step for martingale conversion, you have to go to infinity.
That's right, but because you're assuming that in every step you're reducing the gap by epsilon, that's what gives you the bound number of steps. So it's a martingale convergence where in every step. I'm just thinking
what you're saying, yes. So actually, I sort of said to you, this implies that the thing is, what was the name, bounded? Totally bounded. It doesn't quite give completeness. And to turn that into completeness, what you actually need, if you look at this proof, we refined partitions. So if I had started with some other partition, so you can always say, if you give me a graphon and a partition, I can refine, I find a refinement by multiplying the number of classes by 4 to the 1 over epsilon squared, so that this still holds, right? Because this, if I just had an additional condition that your P should be a refinement of some original Q, well, I could just take these guys and make them also refinements of Q at the cost of having more classes. By a factor of the classes in here. So you can prove the same lemma by saying there's sort of, so you can choose, let's say if you replace K by 2 to the I or something, I can show the delta cut of W and WBI smaller equal than whatever. Okay, where this is now on 2 to the I classes. And these are refinements of each other. And then you know that these guys must actually, by multiple convergence, converge back to W almost surely. So that, I mean, I'm just hinting at, and that you can use to actually create subsequences of convergent sequences to show that essentially this lemma implies not only total boundedness, but actually compactness. And with that, I think I have given you sort of a hint of these proofs. If you want, you're welcome. The papers are both published. One of them took 4 years to find a referee who was able to read it. So one is in 2008, one is in 2012. It's just 100 pages. You can read it in some afternoon. Okay, so thank you very much for being so patient with me.
So in the end, you said this Fries-Kahn proof is easier for you because you came from the original Samarati lemma proof. If it's a kind of now refined, not very original, but the textbook proof, goes similar way in some sense. You know, it's just the combinatorics terminology.
Yeah, but the combinatorics. So this is also sometimes called the weak regularity. So I'm just asking that in the cut norm, it's a close approximation. In the regularity lemma, I will ask that between each of the classes, it's a good approximation. So effectively, you multiply your errors by K squared or something like that in this thing. And now you can imagine how this doesn't work as well anymore because your your errors blow up at the same time you do this, and you have to sort of do this more carefully. And if you do it right, you will get actually a so-called tower in epsilon. So you get, instead of 4 to 1 over epsilon squared, you get 4 over a tower in 1 over epsilon squared. You know what towers are? You get e to the e to the e to the e, 1 over epsilon squared many times. So this becomes, I couldn't present it that easily here, because then you have to really sit down and write on. In the end, the original proof is as easy as this, but the original setting was so general or a little bit stronger. But for us, we don't need, this is enough. This is actually equivalent to compactness, and the original one gives you a little more, which we don't need. Other questions? Okay, you can pester Jennifer with some. Okay, have a good lunch.